Hi, my name is Dr. Andrew Cullen from the University of Melbourne, and I'm here to present our ICML2024 paper, ET2 Certifications, Robustness Certificates Yield Better Adversarial Examples. This work was performed by myself in collaboration with Shiji Liu, Paul Montague, Sarah Afani, and Benjamin Rubenstein, who are all from the University of Melbourne in Australia, with the exception of Paul Montague, who is from Defence Science and Technology Group, also in Australia. So certificates allow us to construct a measure on the lowest bound distance between some sample point x and any possible adversarial example x prime, subject to some LP norm distance. So in doing so, we're able to forbid the worst adversarial examples. If we can construct a certificate for a sample that says no adversarial examples exist within a radius of 0.5, that means the smallest, most difficult to detect adversarial perturbations, those below a size of 0.5, cannot exist. So it makes it more difficult for gives us more confidence in our model's behavior and our model's robustness under potential attack. It also allows us to rank samples by potential risk. So if we have some samples that certify at 0.1, those might be considered to be very high risk because there's a very small guarantee associated with them. And we might want to process those samples differently than samples with a much higher certification of, say, 1 or 2 or 3. Where we can really be confident that it's going to take significant effort for an attacker to construct an adversarial perturbation that changes the output behavior of our model. So we might pass these different risk level samples through different processes, some having human intervention, some not having human intervention, and really allows us to craft our response to securing a machine learning model on a sample by sample basis. Now, many mechanisms exist for constructing these certifications, but one of the most common is known as randomized smoothing, which constructs bounds on the behavior of a function f based upon estimated expectations that are constructed using a Monte Carlo mechanism with noise drawn from the normal distribution. Now, while other mechanisms do exist for constructing certifications, randomized smoothing is quite nice and quite unique in that it's embarrassingly parallel and requires no modifications or restrictions to the interior behavior of the model. All that is required to perform randomized smoothing is to change the input and process the output. Nothing in between actually influences the process of constructing a certification and allows it to be applied in a really general sense. For the remainder of this work, we're going to be talking primarily about certification mechanisms that were constructed using randomized smoothing. However, in our paper, we do show that our approach generalizes to other certification approaches that do not use randomized smoothing. So what we were motivated by in this work was the question of what would happen if you wanted to attack a model that incorporates a certification mechanism. It's important to remember that certifications don't prevent attacks. All they do is they provide a measure of how close the nearest possible adversarial example could be, and as such, they do not obviate the existence of potential adversarial examples. It's just that an adversarial example must sit outside the certified radii. That is all that the certification scheme provides us. And what we realized as we were performing this work is that it's not only that certified models can be attacked, the release of a certification allows better attacks to be constructed. The attacker can exploit knowledge of the certification to make better attacks, make faster attacks, make more difficult to detect attacks than any other technique. And this is the real magic of our approach. Now, to be clear, what we're talking about here is we're talking about attacks on the aggregated expectations at the output of the model. So this differs from other attack techniques of processes that are similar to randomized smoothing, like expectation over transformation, which attacks individual samples prior to aggregation. We are strictly considering an attacker that has visibility of the aggregated output rather than all the individual draws under noise. And so our attacker only has the ability to influence the original input sample, not anything of the not any part of the process after the addition of noise. So to explain how an attacker might exploit the existence of a certification, let's consider a llama classifier that takes an input and determines if it is a llama, which results in the blue class, or it is something other than a llama, the red class. So if we might start off with our original input image I and pass that through a model, and we can construct a certification associated with that. So in decision space, that is this image 1 here, and the certification associated with it is the dashed line going around image 1. As an attacker, knowing that that certification exists tells us that no adversarial examples can exist within that region. And so if no adversarial examples can exist within that region, there's no reason for us to stay within that region for an attack. So we might want to take a large step based upon our gradient-based information to point 2, where we will again construct a certification. So we now construct this new certification, again the dashed line, and this tells us again that point 2 and all these points within this ball around point 2 must predict blue rather than red. So they are the clean outputs, not the perturbed change class outputs. These are the outputs that we would get from the original input rather than the changed output that an attacker might want to influence. So at point 2, we'll again realize, okay, all these points within the certified radii can't be adversarial examples, so we want to take a step outside that, and in our gradient-based approach, this takes us to point 3. Point 3 is now an adversarial example. We can construct that. But if we pass that through the model, that adversarial example still has a certificate. This is one of the the paradoxes of certifications in that adversarial examples still have certificates. And so that certificate is now this red dashed line. Crucially for an attacker, the attacker now knows that everywhere inside this ball is an adversarial example. So if the attacker wants to construct an adversarial perturbation that minimizes the distance between the resultant adversarial example and the original input, they just have to find the nearest point within the ball surrounding point 3 to our original input, point 1. And so if we do that, we can take this step to point 4. And if point 4 does not have a certificate associated with it, then that tells us that we are as close to the decision boundary as we can possibly be, while still maintaining a prediction of class 4, of the red class. And so this input image 4 minimizes the distance in the input space between point 1 and point 4, while still preserving the adversarial example class. To provide a little bit more detail on how this is possible, the process we use ends up being remarkably similar to PGD. So, and at first glance, you might even look at this first equation that takes a input of xi and maps it to some new xi plus 1 that is hopefully closer to being an adversarial example. And you might think that this is essentially PGD. There are two key differences. First of all, we are looking at gradients in the difference between the highest and second highest class expectation of the certified output. The reason for this is that this actually acts as quite a nice smooth proxy measure that we can exploit and construct gradients of, and allows us to really optimize our process a little bit and makes things just a little bit easier to calculate. The second change relates to the step size, epsilon. So typically with PGD, we'd either have a fixed step size or we'd have some sort of decreasing step size based upon some convergence criterion. In our approach, what we do is we set our step size in terms of this term rho. Now rho is based upon the intersection between all possible certifications that we've seen before of our blue class in our classifier. So what we do is we take the intersection between all these different balls, and then we try and find the distance in the direction that the gradient-based PGD style attack is suggesting that we go in. It's trying to find the distance to the first point that is not covered by any of the certificates that we've previously constructed. This allows us to prevent any potential limit cycle behavior that might exist. And so what we end up doing is we end up taking this rho ends up giving us the distance to the first point not covered by a certificate, and then we multiply rho by this 1 plus delta term, which makes sure that we take a step outside the certified radii of points that we've previously seen. And that's it. That's the magic of how we try and find an adversarial example. However, when we've found an adversarial example, we can still take these extra steps to now try and refine the adversarial example. Now this may look pretty similar to the previous slide, but there's again two core differences. The first is now that rather than optimizing based upon the expectations, we're now going to optimize on the distance between our original input x0 and our adversarial perturbation xi. So this allows us to basically try and find motion in the direction that's going to minimize the distance between our final sample and our original input. And we take our step size in a way that now ensures that we remain within the intersection between all certificates of the adversarial example class that we've seen. And then we scale the step size by 1 minus delta, which ensures that we remain within the certified radii of points that we've previously seen, or of adversarial examples that we've seen, which preserves the fact that this xi plus 1 must also be an adversarial example. So to demonstrate the performance of our technique, we plotted the success rate of an attacker against the size of the attack that was constructed. So to interpret this plot, for example, this says that at this point here, says that at attacks of size 2 or greater have a 45% success rate. And so what we ideally want is we want our curves for each attack to be as far up to the left as possible. And so here what we've plotted are results for MNIST in the left, CFAR10 in the middle, and ImageNet in the right, and for 2 different levels of additive noise in our randomized smoothing process. Sigma is equal to 0.5 in the top row, and sigma is equal to 1 on the bottom row. Though again, I'll emphasize that this is for randomized smoothing, but our paper also contains results for attacks against other certification mechanisms. Now, these results were plotted for our approach in blue, PGD in red, Carlini-Wagner in green, Deep Full in mauve, and Auto Attack in teal. And so what we see consistently is that our approach, the blue curve, consistently has higher success rates for lower radii than any other approach, which demonstrates that our approach is finding more difficult to detect adversarial perturbations more often. Now, the one other little bit of detail in this plot that I haven't yet explained is this black dashed line. So this black dashed line is the theoretical upper bound of attack performance based upon the robustness certificates that we've constructed. So because we know that the robustness certificates, they tell us that no adversarial examples can exist below a given radii. This is the aggregate set of results for this whole data set. And so this allows us to provide some sort of upper bound. What we can do with this then is we can, if we were trying to use this technique to verify model robustness, is we could look at the difference between this theoretical upper bound and our best performing attack. And this distance gives us the potential difference that the certifications are either underestimating or the attacks are missing potential adversarial examples that might exist. So it gives us a way of really understanding certification performance. And this is one of the nice side benefits of this approach, that this is not just strictly an attack, it can also be considered as a verification approach for certifications. Now, to demonstrate the performance of our attack a little bit more, we've plotted out that we've tabulated the success rate, the proportion of times that our model is the best, the median perturbation radii, the percentage increase over the certified robustness radius, and the time that it took to construct an attack. Now for these, what we've tried to do is we've tried to control for success rates above 90%. So we're trying to see the best performance above 90% for any particular model based upon a large set of hyperparameters. However, if no set of part of the hyperparameters can reach 90% success rate, then we pick the set of hyperparameters that produces the largest success rate. What we can see is that our technique consistently reaches this high success rate. ImageNet's a little harder, but that is kind of to be expected given the dimensionality of the space. Our approach produces the best adversarial example, and by this I mean the smallest adversarial example between 63% of the time and 97% of the time, relative to all the other 4 attacks. It consistently produces the smallest median certification. It takes a shorter amount of time than any approach bar Deep Full, but we'll note that Deep Full is never, except in ImageNet only very occasionally, never produces the smallest adversarial perturbation, and has shockingly low success rates in some of these examples. So excluding deep fall, our technique is producing attacks almost an order of magnitude, or in some cases more than an order of magnitude faster than PGD and Carlini-Wagner, while still producing these kind of significantly smaller adversarial perturbations. Now, the one little result I'd like to kind of emphasize here is this percentage difference to the certified radio. We constructed this to try and control for the difficulty of constructing adversarial examples against different samples, under the hypothesis that a sample that has a small certified radio is going to be much easier to attack than one with a large certified radio if we kind of have a controlled step size. And so what we kind of posited is that this is a good measure for really understanding how certified robust samples behave under attack. And so what we see is that our approach consistently produces a smaller percentage increase over relative to the size of the original samples as compared to any other technique, with, again, more than orders of magnitude difference between different approaches. So this really allows us to control for the potential difficulty in attacking different samples and allows us to really kind of try and produce an average aggregate measure that is as fair to all approaches as possible, because each approach is not necessarily attacking the same samples. In some cases, if we've got a 56 or a 50 or a 60% success rate, these are potentially different samples that are being attacked. So our percentage relative to the certified radius really controls for that. So in summary, based upon this work, there is a clear and present risk to releasing certifications. There is no doubt, based upon these results, that releasing the certifications provides an advantage to attackers. And even if the certifications are used internally, so they're not released, the process may still introduce additional attack vectors, which practitioners need to be aware of. Concerningly, even hiding the hyperparameters used may not be enough. Within our work, we show that if the level of additive noise that is used for randomized smoothing is hidden, an attacker is still able to estimate that level of noise and still exploit the model based just upon the output class expectations. So basically what we've done is we've demonstrated a really novel threat model against certified robustness. The question we now pose to the community is if the risks associated with constructing certifications are worth their benefits. For further details of this, please see our ICML2024 paper, ET2 Certifications, Robustness Certificates Yield Better Adversarial Examples. At this point, I'd also just like to highlight that this work sits alongside two complementary papers by our team. The first, Double Bubble Toil and Trouble, Enhancing Certified Robustness Through Transitivity, was published at NeurIPS in 2022. And this is about how certification mechanisms can be improved upon by using transitivity. And our other paper, It's Simplex, Disaggregating Measures to Improve Certified Robustness, was published at IEEE Security and Privacy in 2024, and considers how we can analyze the performance of certification approaches to really kind of better understand how certification approaches exist, how they can be compared, and how we can potentially improve on certification mechanisms using aggregate information. With that, thank you for your time.